In this lesson, we want to review simplifying radicals. So one of the first steps to simplifying a radical is understanding the product rule for radicals. This rule allows us to multiply two radicals together with the same index. So if I had the nth root of a times the nth root of b, the index is the same. We'd have the nth root of a times b. So again, notice that this part, and this part are the same, right? It's got to be the same index. Then we just multiply the radicands together. So under the radical symbol, you have this radicand multiplied by this radicand. Okay, that's what we have there. So a couple of examples. If I had something like the square root of 2 times the square root of 3, this would be what? Got a square root and a square root. So it's the square root of 2 times 3, which is 6. Okay. If you had a higher level root, it's the same thing. If you had the cube root of, let's say, 7 times the cube root of, let's say, 5, this is the cube root, right? Index stays the same, of 7 times 5, which is 35. So very, very simple process, very easy to understand. What we're going to need to do is kind of reverse this to simplify. So in other words, if I see something like the square root of 40, I want to write this in such a way that I can simplify. So what do I mean by that? Well, let's take 40, for example, and let's factor it. So 40 factors into 8 times 5, and 5 is obviously prime. 8 factors into 4 times 2, and we know 2 is prime. 4 factors into 2 times 2, and again, we know 2 is prime. So what am I looking for? If I have a square root, I'm looking for factors of 40 that are a perfect square. In other words, I'm looking for factors of 40 where their square root is a rational number. So 4 is a perfect square because it's 2 times 2, right? So I can write this as the square root of 4 multiplied by 2 times 5 is 10, so the square root of 10. Okay? Haven't done anything illegal. Notice that if you had been presented with the problem, the square root of 4 times the square root of 10, by the rule we just learned, we could write this as the square root of 40. Now, this wouldn't be considered simplified, but we could still do it. Now, let's erase this. I want you to think about what you can do here. The square root of 4 we just said was 2. So what I want to do to make this more simple is just replace that with a 2. So I'm going to put 2 times the square root of 10. So the square root of 40 and 2 times the square root of 10 represent the same value. It's just that this guy right here, 2 times the square root of 10, is considered simplified. All right, let's take a look at another example. So suppose you had the square root of 54 and you wanted to simplify. Again, just go ahead and factor 54. So we know this is 9 times 6, and you can pretty much stop there. You know 9 is 3 times 3, right? So 9 is a perfect square. 6 is going to be 3 times 2, but nothing you can really do with that. So I could write this as the square root of 9 multiplied by the square root of 6. Let me erase this, get this out of the way. And we know the square root of 9 is 3, so we're just going to write that. So this is 3 times the square root of 6. Again, square root of 54 and 3 times the square root of 6 represent the same number. It's just that this guy right here, 3 times the square root of 6, is considered simplified. All right, we can also do this process with higher roots. Suppose you had the cube root of 128. So the first thing I'd want to do again is just factor the number. And 128, a lot of you do know that that is 2 to the 7th power. But if you didn't, you could start by saying, okay, it's 64 times 2. 64 is 16 times 4. 4 is 2 times 2. 16 is 4 times 4. And 4 is 2 times 2. And so you have 1, 2, 3, 4, 5, 6, 7 factors of 2. Now, if I want the cube root of something, I am looking for factors of this number right here, of this radicand, that are going to be a perfect cube. Meaning the cube root of the number is a rational number. So if I look here, I can do 2 times 2, 2 times 2, and 2 times 2, right? So I would have 1, 2, 3 of those guys. In other words, I would have 4 to the 3rd power, which is 64, times 2. So I could write this as the cube root of 64, which we know is 4, times the cube root of 2. Okay, all I did was break this down Just because it's a cube root doesn't mean the process is any harder or more difficult. It's the same thing. Instead of looking for a perfect square like you would with a square root, you're looking for a perfect cube because you have a cube root, okay? So all we're going to do is just replace this guy right here with a 4, okay? Cube root of 64 is 4, then times the cube root of 2, okay? So again, 4 times the cube root of 2 is the simplified version of the cube root of 128. All right, so for the next one, we have one with a variable involved. So we have the square root of 50x cubed. So the square root of 50 is very easy to simplify. We pretty much mastered that at this point. We should know that 50 is 25 times 2, and 25 is a perfect square. So I could write this as the square root of 25 times the square root of 2. Pretty simple. We know that this guy right here, the square root of 25 is just 5. All right, but we need to deal with this part right here. So off to the side, if I had the square root of x cubed, what does that simplify into? Well, there's a lot of different ways to think about this. First and foremost, can you simplify? The rule is if this exponent here is larger or equal to this index here, yes, you can simplify. So if I have x cubed here, and my index here is a 2, right? I'm taking the square root of that. I want to think about the next exponent going down that's going to be divisible by 2, my index. Why? Well, if I rewrote this as the square root of x squared times the square root of x, this guy right here would simplify to x, okay? How do I know that? Well, again, if I wrote this using exponential notation, this is x squared raised to the power of 1/2. So this is what? It's x raised to the power of 2 over 2, which is 1, okay? That's the simplest way to kind of think about it. Another way to think about it is to visibly write an index here and just say this guy right here, the 2, the exponent there, is going to be divided by this guy right here, the index. 2 divided by 2 is 1, so you would just have one of those guys. So to simplify this, I would break this up and say this is the square root of x squared times the square root of just x, okay? And again, we already know that this part right here can just be written as x. So we're just going to say that this square root of 25 is 5, square root of x squared is x, and then times what's left over. The square root of 2 times the square root of x is written as the square root of 2x. So we end up with 5x times the square root of 2x. All right, let's take a look at another one with a variable in it. So we have the fourth root of 80x to the 9th power. All right, so I'm looking for a number here that is a factor of 80, and that's a perfect fourth, okay? So if I was to factor 80, what would I get? Well, it just so happens I would get 16 times 5, and 16 is 2 to the 4th power. We don't need to go through the whole factorization. So I'm going to write this as the fourth root of 16 times the fourth root of 5, okay? This part right here would simplify to 2, right? 2 to the 4th power is 16, so the fourth root of 16 is 2, right? 16 is a perfect fourth. Then for x to the 9th power, again, we got to think about this. So x to the 9th power, if I have the fourth root of that, first question, can I simplify? The 9 is larger than the 4, so the answer is yes. Now, if I want to do this, think about the next exponent going down, that's divisible by 4. If I think about 9, 9 is not divisible by 4, but 1 down, 8 would be. So I'm going to rewrite this as the fourth root of x to the 8th power times the fourth root of x, right? X to the 8th times x is x to the 9th, so this is completely legal. Now, I can either use exponents, or again, I can just divide this by this. 8 divided by 4 is 2, so this would end up being x squared, okay? So put times the fourth root of x to the 8th power times the fourth root of just x. And again, this guy is going to simplify to x squared. And again, if you want to see that using exponential notation, that's one of the ones that really helps students if they're struggling. If you have the fourth root of x to the 8th power, this x to the 8th power would be here. It's raised to the 1/4 power. Just think about the fact that this guy right here is always going to divide this guy right here. So it's the 8 here, the exponent, divided by the index here. That's why I do that so quickly. When I use my power to power rule, this becomes x raised to the power of 8/4, which is x squared. All right, so now let's go ahead and write this. We know the fourth root of 16 is 2, so we'll put 2. We know the fourth root of x to the 8th power is x squared, so we'll put that. And then times the fourth root of, what do we have left? We have a 5 and then times an x. So times the fourth root of 5x. So our answer here is 2x squared times the fourth root of 5x. All right, so for the next part, let's talk about the quotient rule for radicals. So if we had the nth root of a over b, this is equal to the nth root of a over the nth root of b. So this would help us if we had something like, let's say, the square root of 4 over 9. Right now that looks kind of hard to solve. So you can break this up and say it's the square root of 4 over the square root of 9. So you're attacking the numerator and denominator kind of separately there. The square root of 4 is 2. The square root of 9 is 3. So we get 2/3 as our answer. Okay, pretty simple. So suppose you saw something like the square root of 7/64. So all I'm going to do is just break this up and say this is the square root of 7 over the square root of 64. The square root of 64 is 8. So I would write the square root of 7 over 8. I can't do anything else with the square root of 7. 7's a prime number. Nothing else I could do. So this is as simple as you can make this. Square root of 7 over 8. All right, let's look at another one with a variable involved. So we have the fourth root of 625x to the 5th power over y to the 12th power. Okay, so I'm just going to break this up. So I would have the fourth root of 625x to the 5th power over the fourth root of y to the 12th power. So the denominator is very easy, right? Again, if this guy is greater than or equal to this guy, then think about if they're divisible by each other. So 12 is divisible by 4. I don't need to do anything else. 12 divided by 4 is 3. So I can just write this as y cubed. I'm done. Okay, I don't have to do anything else. Up here, I've got the fourth root of 625 times the fourth root of x to the 5th power if I wanted to break it up. So the fourth root of 625 times the fourth root of x to the 5th power. Now, I know I can simplify here because the 5 is larger than the 4. We'll get to that in a second. The fourth root of 625 is 5, right? Because 5 to the 4th power is 625. So let's go ahead and just simplify this. We know that's a 5. So we would have a 5 multiplied by the fourth root of x to the 5th power over y cubed. Now, how do we simplify this? Again, if this guy, which is a 5, is greater than or equal to this index, which is a 4, we know we can simplify. Again, think about, is 5 divisible by 4? No. The next number down that would be a 4. So I'm just going to break this up and say this is 5 times the fourth root of x to the 4th power times the fourth root of just x over y cubed. Okay? So this guy right here, again, if I divide this by this, I get 1. So we would have 5 times just x, right? It'd be x to the first power. Then times the fourth root of x, and then over y cubed. All right, now let's talk about how we can multiply radicals with a different index, okay? This is something that's pretty tedious, but you need to know how to do it in case it comes up. So if we had something like the square root of 7 multiplied by the cube root of 3, what do? You can't just multiply the radicands together and, throw some index in there randomly. What you have to do is find the least common multiple between the indexes. So if this is a 2 and this is a 3, the least common multiple is 2 times 3 or 6. So I'm going to write this in exponential notation to make it really easy. So this is 7 to the 1/2 power times 3 to the 1/3 power. And all I'm going to do is write this with a common denominator, okay? The common denominator is going to be a 6 because that's going to be my common index. So multiply this by 3 over 3, multiply this by 2 over 2. You're going to get 7 raised to the power of 3 over 6 times 3 raised to the power of 2 over 6. And you can write this in exponent form like it is now, or you can go back to radical form, whatever you want to do. So we can essentially say this is 7 cubed, and we're going to take the 6th root of that, times, we're going to say this is 3 squared, and we're going to take the 6th root of that, okay? And you can even combine them under one radical, doesn't matter, however you want to do it. For most of these, you're going to end up using a calculator anyway. You just need to know how to do it. So what is 7 cubed? That's 343. What is 3 squared? That's 9. So you would have the 6th root of 343 times 9, which is the 6th root of 3087. 3,087. All right, let's talk about one last concept before we wrap up the lesson. So we have something known as the power rule for radicals, and you can see this in radical notation or exponential notation. So if you have a raised to the power of 1 over n, and then you raise this to the power of 1 over m, a stays the same. You're using your power to power rule. Basically, you multiply the exponents, you get a raised to the power of 1 over m times n. In radical notation, if you have the mth root of the nth root of a, basically this radicand here of a is going to stay, right? So when you write your radical here, the radicand is still a. You get your index as the product of these two indexes, so m times n. So suppose we had the fourth root of the cube root of 5. So based on what we just saw, we know we would have a radicand of 5. And we know we would just multiply these indexes together. So 4 times 3 would be 12. This is the 12th root of 5. But again, if you're struggling, you could start out by writing this inside guy right here as 5 to the power of 1/3. And then this guy is being raised to the power of 1/4, right? So this guy, 5 stays the same. Power to power rule, 1/3 times 1/4 is 1/12. 5 to the 1/12 power is the same thing as the 12th root of 5. All right, for the last problem, we're going to look at the 7th root of the square root of 14x. And again, all I'm going to do is I'm going to take this guy right here, this 14x. I'll write that as the radicand. And then for my index, this guy is a 2, this guy is a 7. 7 times 2 is 14. I'll have the 14th root of 14x. Again, if you're struggling, you can write this as 14x. This whole guy is going to be raised to the 1/2 power. And then that's going to be raised to the 1/7 power. So this would be equal to 14x would stay the same. And this would be raised to the power of 1/2 times 1/7, which is 1/14. This whole thing would be in parentheses. So you could really write this as 14 to the 1/14 power times x to the power of 1/14, which is essentially what we have here, right? If it's inside of parentheses like this, it looks like that. But this is the same thing. They're equivalent because I could write this as the 14th root of 14 times the 14th root. Let me make that better. Again, the 14th root of x. But you wouldn't want to do that, so we would just leave our answer in this format here and say that this is the 14th root of 14x.